All right, let's jump right in. Today, we're going way back to the very beginning of an idea that, honestly, promises to change everything. We're talking about a foundational paper from 1982 by a physicist named Paul Benioff. This was the paper that first proved, with some serious math, that a quantum computer wasn't just some sci-fi fantasy, it was actually possible.
I mean, just think about that question for a second. It sounds like it's ripped straight from a modern blockbuster, right? Could you really build a computer out of the fundamental fabric of the universe itself? Could you harness the super weird rules of quantum mechanics to actually perform calculations? A machine where the bits aren't tiny switches, but individual atoms.
And believe it or not, the answer was yes. While a lot of people were just kind of kicking the idea around, Paul Benioff went and published a paper that laid out the entire mathematical framework for how a machine like that could work. Now, he didn't build it, but he proved it could be built, and that changed everything.
To really get why this paper was such a big deal, we got to understand the problem Benioff was wrestling with. It wasn't just about making computers smaller or faster. No, it was about a fundamental limit that physicists thought was just a law of nature. The energy cost of thinking, of computing.
See, before the 80s, the common thinking, and this goes all the way back to the 1960s, was that any act of computation was physically irreversible. To do a calculation, you had to erase some piece of information, right? Like clearing out a memory register. And that very act of erasing, physicists were convinced, had to waste energy as heat. It was just a fundamental cost. So by its very nature, computation had to be inefficient.
But a crucial piece of the puzzle had already been put on the table. Back in 1973, another physicist, Charles Bennett, showed that you could theoretically design a computer that was reversible, one that didn't have to erase information. And this opened the door to a truly mind-blowing idea, a perfectly efficient computer that wastes zero energy. Benioff saw this idea and just ran with it, straight into the quantum realm.
So how do you do it? How do you even begin to design a computer that plays by the bizarre rules of quantum mechanics? Well, his approach was brilliant. He decided to build a model from the ground up. And you should think of it less like a modern silicon chip and more like, well, like a quantum abacus. Benioff's core idea was to create a complete quantum mechanical model of a Turing machine. Now, a Turing machine is just this abstract, universal idea of any computer you could possibly build. It's got a tape, a little head that reads and writes, and a set of rules. Benioff's mission was to describe every single one of those parts using the language of quantum physics.
So what's the hardware for this quantum abacus? Well, in his paper, he describes it as a two-dimensional grid, a lattice, of what he calls spin-1/2 systems. The easiest way to picture this is just a grid of tiny quantum particles, maybe like electrons, and each one has this fundamental property called spin. These are the beads on his quantum abacus.
And this is how you store information. It's pretty simple, actually. Just like a regular bit can be a 0 or a 1, the spin of each particle can be in one of two states, spin up or spin down. So you just decide that, say, spin up means 1 and spin down means 0. Boom! You can now encode a whole tape of data just by setting the spins of a line of these particles.
Okay, but having beads on an abacus is one thing. How do you get it to actually do anything? This is the absolute key. Benioff designed a master equation, something physicists call a Hamiltonian. You can think of the Hamiltonian as the engine, or maybe the quantum rulebook. It's a chunk of math that dictates exactly how the spins on that grid have to change over time, forcing them to flip in a perfect sequence that mimics a real computation.
And what's really fascinating here is that Benioff didn't just come up with one engine. Nope, he proposed two totally different ways to run his quantum computer. We're going to start with the first one, which is a little more intuitive. Let's call it the clockmaker's computer.
So let's just quickly compare these two models. First up is the clockmaker's computer. It's called time-dependent because it needs an external switch to get from one step to the next. Its evolution is local. It only ever thinks about the very next step. Then, you have the self-winding computer. This one is time-independent with a really complex self-running engine, and its evolution is global. And that, my friends, is where things get super weird.
The clockmaker's model works in this very deliberate 1, 2, 3 rhythm. In each cycle, some external agent, our clockmaker, has to come in and flip a switch to turn on the Hamiltonian that records the current state. Then, they flip that off and turn on another one to do the actual calculation. And finally, they turn on a third one to move the machine's head to the next spot. It's very step-by-step, driven by an outside force. And this is a perfect example of what he means by time local. Between each tick of the clock, the computer's state is just a quantum mixture of the step it just finished and the one it's about to start. That's it. It has no idea about steps way in the past or way in the future. It's just a straight line moving forward one step at a time.
But what if you could get rid of the clockmaker? What if you didn't need anyone turning the crank? Benioff's second model does exactly that. This version is completely autonomous, kind of like a self-winding watch that, once you start it, runs the entire calculation all by itself.
This is the time-independent model. For this one, Benioff builds a single, unbelievably complex Hamiltonian. This one engine has all the rules for the entire calculation baked right into it. So you just set up the computer in its starting position, let this master Hamiltonian take over, and it just goes. It evolves completely on its own, clicking through the calculation with zero outside help.
And this is where the pure magic and the deep strangeness of quantum mechanics really kicks in. To explain how this self-winding watch works, Benioff describes its state between the ticks. As he puts it, the system exists in a linear combination, which is just quantum speak for a superposition, of states that represent all stages of the computation.
Okay, so this is the really wild part. Get this. While the clockmaker's computer is just moving from, say, step 4 to step 5, the self-winding computer does something completely different. In that tiny instant between those two steps, it exists in this ghostly quantum superposition of every single step of the calculation, all at once. Step 1, step 2, step 20, the final step. They're all there at the same time. That's what Benioff called time global. It means the computer's entire past, present, and future are all kind of smeared together in this single probabilistic haze. It's just mind-bending.
So, okay, we've got these two models. One is kind of practical and step-by-step. The other is profound and deeply weird. But what was the point of it all? Why are we still talking about this 1982 paper today?
Well, first and most important, it was a rock-solid proof that computation and quantum mechanics could actually work together. It showed that a reversible quantum computer could, in theory, run with zero energy waste, completely shattering that old idea. Benioff even showed his self-winding model could run near the absolute quantum limit of efficiency. Bottom line, this paper was the mathematical green light for the entire field of quantum computing.
Now, it's super important to understand what this paper was and what it wasn't. This was not a blueprint for building a quantum computer you could buy at a store. Benioff himself said the model would be incredibly fragile. This was a proof of principle. It was a rigorous mathematical argument that said, hey look, the fundamental laws of physics actually allow for this. It changed the whole conversation from if to how.
And that really brings us right up to today. Benioff's paper proved it was possible. He laid the theoretical bedrock. The massive challenge for scientists and engineers over the last 40 years has been turning that theoretical possibility into a practical reality. So the question that's still hanging in the air is, what's the next great breakthrough that's going to take us from a proof on paper to a machine that really, truly changes the world?